everybody, my name is Madison Brady. I'm a grad student at the University of Chicago, and today I'm going to be talking to you all about a survey that I've been performing with MAROON-X to perform precise mass measurements of a volume limited of M dwarf planets with TESS transits. Just as a little start, this talk is going to be on an ongoing survey, so these results are somewhat preliminary and are likely going to be due to change as we sort of update and add additional data to our sample and update our analysis techniques. So just keep that in mind. So to start out, I just want to say that I'm sure most of you are familiar with this, but M Dwarfs provide one of the, I'm getting some sound from the computer. Okay, sorry. I'm getting like some feedback over here. So M dwarfs provide us with the best opportunity to study rocky planets, as M dwarfs have the largest radial velocity signal, as well as just transit photometry signals. There's going to, I particularly want to call attention to the JWST transit photometry, where we expect that signal transit, JWST transit data. I'm really sorry, I'm having some technical issues up here. I'm getting like a reverb, a pretty loud reverb. Like I'm getting like a reverb up here on the computer.
I think it's just the computer.
Okay. Sorry about that. I was a reverb on my computer. Maybe I'll just start over. M dwarfs provide us the best possibility to minutes as general signal velocity around for these small planets is the largest around the smallest possible stars. We also expect that for actually atmospheres of these planets, which we're going to need to do, we want to talk about whether or not these planets are habitable. JWST signal transit SNRs are expected to be maximized only around very nearby M dwarfs. In addition, however, M dwarfs provide a problem as we don't necessarily expect planets and dwarfs to be exactly the same as other type stars. To stars, I mean a lot smaller. You can see in this figure on the left, which is generally just the results of some that, while they might nowadays be in the habitable zone, were actually dramatically interior to both the habitable zone and the snow line as they formed. They'll typically have extremely low volatile contents. And in addition, as you can see in the plot on the right, M dwarfs in general just emit a larger fraction of their radiation as XUV, and also our planets are expected to lose a large fraction of whatever volatiles they were able to form over the course of their lifetimes. However, there may still be hope. There may still be volatile rich planets kind of nearby into M dwarfs at sort of period ranges that we can actually access with transit photometry. And that is actually kind of shown in this figure on the study done by Raphael Luque and Henri Paillet in 2022, where they basically just did a search and looked at every single well-characterized M dwarf planet. And in general, they found, as you can see in this figure, that the vast majority of M dwarf planets fall in one of two trends. You can see that a lot of them seem to be consistent roughly with Earth-like composition, while another population of them seem to be roughly consistent with being about 50% water. Now, you might be wondering, how are we getting all these 50% water planets if I just said that we don't really expect volatile rich planets to form in this regime? There's a couple of potential explanations. One of the big ones is that some people might just say, oh, these are just rocky planets with big hydrogen envelopes. Now that's something that we can kind of argue over and maybe follow up with JWST to really figure out. But another potential explanation is that these objects actually formed at much larger orbital separations and were able to migrate inwards. This figure on the right is the result of some new generation planet population synthesis models, which in general showed that we can expect volatile rich planets to be seen even at very short orbital periods around M dwarfs, but these are objects that actually migrated inward from beyond the snow line over the course of the system lifetime. So what I'm interested in doing is kind of boosting our understanding of these objects and really trying to characterize the masses of many M dwarf planets that are sort of accessible with follow-up surveys to see, like, do we see a lot of planets with these compositions? And maybe what else can we learn about planetary compositions before we start doing the really expensive follow-up surveys? So this slide just in general kind of describes the actual specific survey requirements. Specifically, we are following up nearby TESS objects of interest that are verified and within 30 parsecs around planets that are stellar stars that are consistent with being M Dwarfs, with the goal of achieving roughly a 10 to 20% mass density and composition measurements, because at that point, our errors will be guided primarily by planet radius measurements, which we can't really improve beyond a certain level. And that 20% will be good for atmospheric characterization with JWST. Currently, there are 34 planets in the sample, and we have data already contributing to 4 publications so far that have all been able to achieve very precise mass measurements on planets in this sample. So we've already seen in publications that our data is capable of holding up. And in general, my plans in the future are to publish all of this radial velocity data as well as all of the planet masses over the next couple of years. Andreas talked about MAROON-X on Monday, so I'm not going to spend too much time belaboring this point, but I did figure I probably should have at least one radial velocity plot in this talk, so that's what's on the right. But MAROON-X is a stabilized fiber-fed spectrograph on Gemini North with an optical to sort of red optical wavelength coverage. We already have collected over 600 observations of survey targets since 2020, and in a survey that is still ongoing and planned to be ongoing for another couple of years. Again, this figure on the right is just one of the unpublished data sets from our sample. I would like to note that we don't really use that this particular image doesn't make use of any Gaussian processes or anything like that. And you can already see we're able to achieve like a semi-amplitude radial velocity error of around 10 centimeters a second. Another interesting tool in our back pocket is, since our survey is basically primarily guided by the biases of TESS, as every single target in our sample is something that TESS found, and MAROON-X is actually capable of observing every single target in that sample. If we understand the completeness of TESS, we can actually understand the completeness of our sample itself and start to say things statistically about the frequency of the masses of the planets in our sample. So we can actually start to use this sample to characterize sort of the mass function of planets, which will be very interesting. Though of course, since these are just the results of some fairly simple simulations, I'm sure at some point TESS is gonna release an awesome study where they do a really careful completeness analysis. So this is a bit of an estimate, at least for now. This figure here is the mass radius diagram of all of the planets that are currently in our sample. I will say we include all of the radial velocity data on the samples in addition to any new and unpublished MAROON-X data. So I would say, since not all of these are really published results, that things are probably going to change around a little bit as we continue to sort of collect more data. So I'm not going to call attention to any particular data point on this plot, but I think the trends are generally pretty reliable. Something in particular I want to point out is that we've already been able to achieve a 10% mass error on roughly half of the targets in our sample. So while that sort of 10 sigma measurement may sound insane, it's actually very much possible, and in fact already achieved for a lot of our targets. And even for those for which we haven't, around 2/3 of the sample already have a 20% or better measurement, which will already put them in the place where JWST follow-up is worthwhile. Just to call attention to a couple of particular trends, this first one, if you notice, there's a lot of targets that fall right around that Earth line, which is 1/3 iron, 2/3 rock. You can see that we already have a lot of planets that seem very close to being composed like that of the Earth. And actually, if you go through and measure the core mass fractions of these planets, even with fairly wide priors on things like assuming the iron content, we find that the majority of the rocky planets in our sample have core mass fractions roughly consistent with that of the Earth. So even though we see a pretty wide distribution of core mass fractions in our own solar system, it at least seems like the universe likes to form Earths. Another thing I want to point out is you might have noticed that despite that previous study where I showed you all those water worlds, we're not really seeing too many in our sample itself. I think my particular theory about this mostly has to do with the orbital periods we're sensitive to. While that other study I pointed out included objects from Kepler and K2, we're only looking at TESS targets. And since the TESS sector length is fairly short, we generally don't really expect to see too many volatile-rich planets. Even if you go, I went and looked at some simulations and generally was able to find that at shorter orbital periods, there are just fewer volatile-rich planets that are actually able to get in that far. So at the level of around 10%. And you can see that that seems to be roughly consistent with what we're seeing here, though there are, of course, a lot of planets that maybe if we tighten up those masses a little bit might look more volatile than they do right now. The last thing that I'm really excited to talk about is what I refer to as the mass valley. Around 4 to 6 Earth masses, we kind of notice that there seems to sort of be a valley where we don't have as many planets noticed. And even if we go back and look at that previous sort of literature search, you see that there's still an underdensity in that regime, though it seems to be shifted slightly, but that again might just be due to their different period range that they were looking at. And if I then try to go back and use my sort of preliminary estimates of the TESS completeness and try to actually calculate the frequency of planets as a function of mass, we see that that valley still persists, though since we haven't actually observed every planet in our sample at this point, it's possible that this plot may change a little bit with time. The first potential explanation that I have for this just has to do with, you could assume that maybe the low mass peak is rocky planets and the high mass peak is icy planets. However, even just looking at this figure here, which is just like all of the precisely characterized M dwarf planets again from that 2022 paper, you can see that there are a lot of planets that seem to be very confidently on that rocky line that are relatively high in mass. Well, there are a couple of planets that appear to be pretty volatile rich that are fairly low in mass. So that doesn't seem like the explanation. My personal favorite explanation has to do with migration. We see that there are perhaps like this figure, once again from population formation simulations, shows that a lot of planets form at the ice line and migrate inwards, but only the highest mass planets do that. So if we're looking at really short orbital periods, we're only going to be seeing some pretty high mass volatile rich planets. And then those lower mass planets are probably the rocky ones that formed in situ. And then we can kind of imagine there's a tail off where, you know, most of the rocky planets have low masses, but there are some high mass ones. And then of the volatile rich planets, depending on the size of the host star, you can actually get some relatively small planets moving in. So that seems to be the explanation, though I'm not 100% sure. And I would love to hear anyone else's opinions on this. Since I'm low on time, I'm just going to put up my summary slide. Thank you, everybody.
So I'll look for questions, but I also want to ask members of the SOC to maybe come to the side of the stage for the next announcement. Questions? So I'll ask a question. This seems like it's been an extraordinarily successful large survey, and we're looking forward to the final results, of course. But I wonder if you could say if there are plans for a follow-on survey of similar targets or different targets for MAROON-X?
At least at this point, we're mostly focusing on this survey. Something I would really love is if we could get better coverage in the Southern Hemisphere, though unfortunately that wouldn't be with MAROON-X and would probably introduce its own set of additional biases. But right now we're really hampered by the fact that since we can only really look at one hemisphere, there's a lot of really interesting targets in the Southern Hemisphere that we currently just really can't look at.
All right, well, thank you, Madison. That was a terrific talk.